Okay, welcome to part 1 of our lecture video series from Wednesday, May 3rd. And let's begin wrapping up our conversation about pressure relationships of gases. So if you remember our discussion from Monday, we noted that pressure and volume are inversely related. So again, when we're looking for these pressure relationships, we're talking about things that are going to affect the number of collisions that are happening in a sample of a gas. So for example, if I were to take a sample of gas in a piston at some initial volume V1, so remember this is full of gas particles that are constantly bouncing around here, according to kinetic molecular theory. And if I were to take this piston and compress it so that the volume in which my gas has to occupy, V2, is smaller than its original volume, then I have that same number of gas particles now closer together, meaning that they are more statistically likely able to encounter one another and thus collide with one another and the walls of the container and exert forces, which sum up to us talking about pressure, right? So as we see a decrease in volume, we will see that pressure increases. This is where we get the idea of our inverse relationship. And remember, Boyle's law said that this inverse relationship can be expressed mathematically by saying that the product of pressure and volume is equal to a constant. And for us, this is just kind of the mathematical structure of an inverse relationship. So this is where we wound up on Monday. So that was looking at pressure and volume. What else? So let's ask ourselves, what other things could affect the number of collisions and thus the pressure of a sample of gas particles? So let's think about pressure and temperature. So if I have, let's say, a fixed container at some initial temperature full of gas particles, these gas particles are all going to be moving with some initial kinetic energy. So initial kinetic energy, Ke sub I. And if I keep this volume constant, but I increase the temperature such that the temperature of my new system is larger than my temperature of my gas, how it was originally, then my kinetic energy of all of these gas particles is going to be higher because all of that thermal energy is going to be transformed into kinetic energy. So these gas particles, which are moving, let me get my laser pointer, which are moving around with some kinetic energy at some temperature. Remember, the temperature of a gas sample has some direct correlation to the kinetic energy of our gas molecules according to kinetic molecular theory. So if I'm at some temperature, all of these particles have an average kinetic energy that is set. And if I increase that temperature, I now have more thermal energy available for my molecules to transform into kinetic energy, meaning they are going to be moving around faster. And if they move around faster, then the statistical likelihood of encountering one another and then colliding with both molecules and the walls of the container is going to increase. So because my kinetic energy is increasing, if I increase my temperature, then I'm going to have more collisions at my higher temperature than I do at my lower temperature. I like to think about this in terms of old school like zombie movies. So I don't know if you guys have ever seen something like Day of the Dead, right? One of the first zombie movies. The original zombies are really slow walking, right? They're, not like the crazy, vicious, fast zombies that you and I know in modern pop culture today. So if you want to think about these gas particles like old school 1970s horror zombie movie zombies, they're moving around pretty slowly in a room, meaning the likelihood that a zombie will smack into or run into another zombie or bounce into the wall is gonna be pretty low, just because these zombies are moving pretty slowly. Now compare that to like the modern day zombies seen from like Last of Us or 28 Days Later. Those are fast running zombies, right? So if I have a bunch of those crazed zombies in a room, they're going to be moving at much higher speeds, right? Running around, frenzied, meaning that the likelihood that these zombies are going to run into one another and run into the wall is going to be much higher. And that's because they had more kinetic energy, right? If they were moving faster, they had more kinetic energy. Here, we're supplying more kinetic energy to our particles by means of increasing the temperature. So if I increase my temperature, and then I see an increase in our collisions, which means that we have to see an increase in pressure, then let's think about what that means. So if I were to increase the temperature, then I would also be increasing the collisions, thus increasing the pressure. Or vice versa, if I were to decrease the temperature, I would be slowing those molecules down, resulting in fewer collisions, so I would have a lower pressure. So notice, for a change in one, there's the same type of change in the other. This is a direct proportionality. This is what's modeled by our linear function. And remember, direct proportionalities have the structure of their quotient being equal to a constant. So since this is a direct proportionality, I could say that pressure over temperature is equal to a constant. And congratulations, from just kind of rational, logical thinking, we have managed to derive what's known as the Gay-Lussac law. So, Gay-Lussac. Of the gases, which is part of the life's work of these two French dudes in the 18th century. So, yay, in about 5 seconds, we did life's work of some two dudes. Fun. All right, so that is pressure and temperature. And just like we did with Boyle's law, I want to kind of show us the consequence of saying that this is equal to a constant. So yes, that's the mathematical structure of a direct proportionality. But what this means is that if I've got pressure at some initial condition and a temperature at some initial condition, then that has to be equal to a new pressure over that new temperature, which is equal to some other pressure over some other temperature, and so on, because these are all equal to the same constant, the proportionality constant that relates pressure and temperature. So that's one of our pressure relationships, pressure and temperature. There is one more that I think we could come up with that will, one more property that will affect our pressure or our number of collisions. So let's look at pressure and moles N relationship. All right. So let's think about what would happen if I've got a gas in some container. Now it's a circle, ooh. And it's at some constant temperature and some constant volume, meaning the only thing that I'm going to be changing is the amount of gas in my container. So pretend for me, please, that these are the exact same container. In fact, how I use technology, to make it that way. So we're, again, the same temperature and at the same volume. And let's suppose that what I do is I add gas, meaning I increase the quantity of gas by adding more moles of gas. So let's say I had 1, 2, 3, 4, 5, 6, 7, 8, 9 originally. And now let's say I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 moles of gas. Let's imagine what might happen to the number of collisions now that we have more gas present in our container. So again, we're thinking about the statistical likelihood of molecules encountering one another, colliding, and then possibly colliding with the sides of the container that the molecules are found in. So I like to think about this kind of relationship by thinking about, like crowded concerts or crowded spaces. So let's assume that you are at some concert venue and it's like a small, really cool hipster basement venue, right? Little local place. And the volume and the temperature of that room, that little venue, is the same. But let's say that it's just some like small name band that's at that concert and only a couple of people show up. The ability for you to move from your seat to the stage to go see the band is going to be much easier because you've got fewer people in your way, right? You can kind of navigate through or move through that space and be unlikely to collide or encounter or run into somebody else just because there are fewer people at that venue. Now, let's say that same concert venue is booked for like some really popular famous band. That means that a lot more people are going to be in attendance. And so the possibility of you being able to go and get up to that stage is going to be a lot harder because you are statistically more likely to run into other people on your way to heading toward that stage. So we've got the same amount of kinetic energy, right? We've got a constant temperature. So all of these are moving with the same amount of kinetic energy. They're just now moving amongst a higher density or higher quantity of gas. So as we add gas, we would see more collisions compared to when we had fewer particles of gas. There'd be less collisions. And again, if we have more collisions, then that means that our pressure is higher. So kind of putting that into the language we've seen here, if the moles of our second system or the second condition is greater than the moles of gas initially, then the pressure with that system with the new amount of moles also has to be greater than it was originally because we have more collisions. So writing this out mathematically, we could say that an increase in the quantity of gas results in an increase in the pressure due to there being a higher likelihood of collisions. Or we could say the opposite is true. A decrease in the quantity of gas is going to result in a decrease in the pressure of a gas because the fewer particles, the less likely it is for collisions to happen. And notice since these trends are the same, meaning a change in one results in the same type of change in the other, this is another example of a direct proportionality. And remember, direct proportionality says that the quotient of two variables is equal to a constant. All right, again, congrats, just from kind of common sense. We have derived something called Avogadro's law, which relates the quantity of gas to the pressure of that gaseous system. And we can say something very similar that we have for Boyle's law and the Gay-Lussac law, which is because this quotient is always equal to a constant, then I can relate the pressure and quantity of a gas at various conditions by setting them equal to one another, because all of these proportions of pressure and moles are equal to the same constant, that proportionality constant that relates them. So in summary, for our pressure relationships, we have that pressure and volume are inversely related. We have that pressure and temperature are directly related. And we have that pressure and moles are directly related. Now, the fun part about this is I can put all of these together into one big relationship, meaning I can put this all together into one mathematical structure that shows that pressure and volume are inversely related, while pressure and temperature are directly related, and pressure and moles are directly related. So let's start with pressure. So I'm going to write pressure, and I know that it's going to be related directly to some stuff, so there's going to have to be a fraction here. So I've got pressure, and then it looks like the product of pressure and volume is needed in order for us to get our Boyle's law back. Let me just go back and check my color coding, otherwise I'm going to go crazy. Let's call it purple. Here we go. Okay, so we have a product of pressure and volume. Now, let's see here. When we're looking at pressure and temperature, we should have pressure in the numerator, which we do here in this expression, but then temperature needs to be in the denominator. So I'm going to put my temperature variable in the denominator. And then my moles also need to be in the denominator. And all of these are going to be equal to some constant that relates pressure, volume, temperature, and moles. So putting this kind of all together in a nice tidy little box, PV over NT is equal to a constant. Now, we're going to kind of hold on to that because it's coming up. So let's keep a look at this equation. This is kind of combining all of our pressure relationships so far. And remember, just like I said with our other things, this means that I could look at initial conditions of pressure, volume, moles, and temperature. And as long as I've got this plugged into the right mathematical structure, then this would be equal to some new conditions of pressure, volume, moles, and temperature, or some other conditions of pressure, volume, moles, and temperature. And these would all be equivalent because these are all equal to some proportionality constant. All right, so in our next video, we are going to take a little closer look at this mathematical structure and use it to relate not just pressure with other variables, but we're going to look at relationships between like volume and moles or volume and temperature. So we're going to use this kind of big fat summary of everything we've looked at so far to help us look at relationships of other gas properties. So that will be coming up in video 2 soon.